Hey everyone, welcome back to more calculus work, and today we're going to be looking at something which isn't particularly difficult. It's section 9.3, relative rates of growth. And here we're going to take our knowledge of limits and put it to good use. You're going to need to have some pretty good knowledge about which functions tend to grow faster than others. Having that kind of a function sense is really going to serve you well once we get into our next section, which is majorly concerned with convergence and divergence. So let's get started. Faster or slower? As x increases in size, a positive function f is said to grow faster than g if f of x is greater than g of x for all sufficiently large values of x. Order the following functions from slowest to fastest. So we've got e to the x power, root x plus 1, x cubed, 10 to the x power, and 2 to the x power. Now, in order for us to do this, we need to have some kind of a function sense, like which of these are actually fast functions. And based on what you know about the curves, you might guess that that the root of x plus 1 doesn't grow as fast as x cubed. Thinking about the way that those curves work, one of those is concave up and one of those is concave down. You would imagine a concave up function is going to grow faster than a concave down function. But let's suppose we have two functions, f and g, and we look at the ratio of those two functions. So if that ratio goes to infinity, that seems to imply that the top function, the numerator, is going to grow faster than the denominator. And that kind of makes sense because, well, if the numerator grows faster than the denominator, whatever we have is going to get more and more positive, bigger. I'm not 100% sure about what we should say about that, but it's definitely going to grow. So if the limit, or if this ratio trends to infinity, we're going to say that the numerator function grows faster. And conversely, if the ratio trends toward 0, we're going to say that the denominator function grows faster. We can use that knowledge to put together something like this. We're going to say that f grows faster than g if f is in the numerator and it grows faster, then this limit of f over g as x goes to infinity should also trend toward infinity. And if the f of x is on the denominator, that tells me that this limit, g over f, should go towards 0. And then as a consequence of this, we have to also say that if f and g grow at the same rate, then the limit has to exist and the limit can't be 0. So that might get some of us in a little bit of trouble, or that might seem counterintuitive, but as long as the limit exists, then the two functions are growing at the same rate. Let's use our newfound conception to figure out which one grows faster, e to the x or x cubed. So we're going to go ahead and make a ratio of x cubed over e to the x, and whichever function that I think is going to grow faster, I tend to put on the denominator because it makes more sense to me to get a limit that's 0, or it feels more satisfying for me to get a 0 limit than a not 0 limit. So both of these functions trend to infinity. So I'm going to use L'Hopital's rule to evaluate. So this limit is equivalent to the limit as x approaches infinity of 3x squared on e to the x. And this limit is still infinity over infinity. So we're going to use L'Hopital's rule again. So this limit is equivalent to the limit as x approaches infinity of 6x over e to the x, using L'Hopital's rule again. This still trends to infinity over infinity. So we'll use L'Hopital's rule just one more time. We get 6 over e to the x, and this should make sense that we get 0 here. Since the numerator is staying the same, but the denominator is growing without bound, we get a 0. So if the limit of the ratio is 0, that tells me that whatever function's on the denominator, e to the x, is going to grow faster than whichever function is on the numerator, x cubed. Okay. So this works for any pair of functions. As long as you can evaluate the limit, you can tell which function is going to grow faster. Now, what about natural log of x and x cubed? Well, natural log of x, that is a downward concavity function, and x cubed is an upward concavity function. So this leads me to believe that x cubed is going to grow faster. But of course, with all things math, you got to prove it. So let's take the limit as x approaches infinity. Numerator is x cubed. No, I'm sorry. Numerator should be natural log of x, because I'm trying to get a 0. That makes more sense to me. We've noted that both of these functions, the numerator and the denominator, trend to infinity. So we're going to use L'Hopital's rule. And this is going to be equivalent to the limit as x approaches infinity of 1 over x over 3x squared. Now, you might be looking at this. And saying, well, that's 0 over infinity. I better use L'Hopital's rule again. But wait. You can simplify this. This is equivalent to the limit as x approaches infinity of 1 over 3x cubed. And that is no longer indeterminate. The numerator stays a 1, the denominator grows without bound, so this limit is 0. Therefore, x cubed grows faster than natural log of x. Transitivity. And this should make sense if f grows faster than g and g grows faster than h. That means f is going to grow faster than h. Transitivity. So based on transitivity, we can order these 3 functions together. So if I remember this correctly, x cubed grew faster than natural log of x, and e to the x was faster than x cubed. So that means that if e to the x is faster than x cubed, and x cubed is faster than natural log of x, e to the x is also faster than natural log of x, which means e to the x is the fastest of the 3. E to the x was proved to be faster than x cubed, and x cubed was proved to be faster than natural log of x. From the above, we can infer that, generally speaking, this is just an inference, that exponential functions are going to grow faster than power functions or algebraic functions. And algebraic functions are in turn going to grow faster than logarithmic functions. That statement right there is meant to build your function sense so you know what kind of functions are fast functions, what kind of functions are slow functions. And that brings us to our important ideas. So we've got the idea that we came up with earlier, where if the limit at infinity is infinity, then the function on the numerator grows faster. And if the limit is 0, then the function on the denominator grows faster. If it's constant, then they grow at the same rate. And then we also had this general thought about which functions grow faster. Of course, logarithmic functions are the slowest functions. Algebraic functions are the next slowest function, and these can be ordered by the power. So a function that is a third order function is slower than a function that is a 10th ordered function. And then finally we come to exponential functions, which are among the fastest functions. And of these, the bigger base is going to grow faster. So 2 to the x is going to grow faster than e to the, other way around. 2 to the x is going to grow faster than e to the x because e is bigger than 2. 5 is bigger than e, 10 is bigger than x, or 10 is bigger than 5, and x at a certain point will be bigger than 10. So x to the x usually is one of the fastest functions we're going to have out there. Okay, let's show that natural log of x grows slower than x plus natural log of x. We're going to set up our limit with the faster function on the denominator. Ooh, I got that backwards. Well, too late now. Now we have the faster function on the numerator. You don't have to rewrite it, just adjust your expectations. We're going to note that this is going to go to infinity. The numerator is going to go to infinity as well. So we can use L'Hopital's rule in order to help us out here. The L'Hopital's rule says we have the limit as x approaches infinity of the derivatives. Derivative of x is 1. Derivative of natural log of x is 1 over x. The derivative of natural log of x is 1 over x. Simplify this, and you get x plus 1 over 1. And this goes to infinity because the numerator grows, but the denominator doesn't grow. So therefore, the numerator, x plus natural log of x, is faster than the denominator, natural log of x. Okay, this one over here. Does the square root of x plus 1 grow faster or slower than 2 to the x? Well, this is a square root function, and we can think of those as power functions or algebraic functions, with x to the 1/2 being the lead power. And then this is an exponential function, so I'm thinking the exponential function is going to grow faster. Let's note that the denominator is going to go to infinity, and the numerator is also going to go towards infinity. So we're ready for L'Hopital's rule. Let's take our derivatives. We've got 1 over 2 root 1 plus x over natural log of 2 multiplied by 2 to the x. Simplify, and we got a whole lot of stuff on the denominator and a 1 on the numerator. So this denominator, each one of these is an increasing function. So this denominator is growing without bound, so this is going to approach 0. So 2 to the x grows faster than root 1 plus x. And now let's take a look at these. Order these 3 functions from slowest to fastest. Look at that typo over there. Don't worry, that'll get fixed. So have an intuition. Which one of these do you think grows fastest? And then test the faster two, and then use transitivity to test the slower two. And then, put it all together. So we've got x to the x, e to the x, and e to the x over 3. Now, in order for me to do this, maybe we should look at the bases. This is e, which is about 2.7 to the x. This is x to the x for the second one, which means that at some point, when x is bigger than 3, then the base will be bigger than 2.7, and this should grow faster than 2.7 to the x. Again, x to the x is one of the faster functions that we have. And the last one you have here, it's probably better if you looked at it as 2.7 to the 1/3 power to the x power. Now this is going to be a number that's smaller than 2.7 because it's a cube root. So this looks like it's going to be the smallest base right here, small base. This is going to be the middle base. And this is going to be the fastest base, or the largest base. So let's compare the two smaller functions. And we think that e is going to be faster than e to the x over 3. So this is e to the x, and the numerator is e to the 1/3 to the x. Okay. And look what you can do here. Since these two have the same base, let me rewrite it with the same base. Since they have the same base, we can actually use properties of exponents to say that this is 1 over e to the 2/3 x. Now 2/3 is 1 minus 1/3. That's going to go to the denominator. A little bit of more advanced way of thinking about the functions than you did or the powers than you did in Algebra 1. And now this clearly is going to go to 0 since the denominator is growing, but the numerator is not growing. So e to the x is faster than e to the x over 3, which we kind of knew already, but we just had to prove it. Let's take a look at the two faster growing functions, and we have the limit as x approaches infinity of e to the x over x to the x. Now what we can do with this, these are different bases, e and x, so we can't use the trick that we just utilized before, but we can do something else. We can take the limit as x approaches infinity of e over x to the x power. So we've kind of gathered all the power together over here, which is okay since we have single term numerator and single term denominator. Now what happens here? The power goes to infinity, clearly. But the base goes to 0. Now 0 to an infinite power, that's not one of our indeterminate forms. So we don't have to use L'Hopital's rule here. As our base gets closer and closer to 0, then this is also going to go closer and closer to 0. So this limit is equal to 0. Therefore, x to the x is faster than e to the x. So we're going to order these from slowest to fastest. So which was the slowest one that we found? The slowest was e to the x over 3. And faster than e to the x over 3 was e to the x. And faster than e to the x was x to the x. So here it is from slow to fast. So that's all we have today. Hopefully those two tricks on how to look at limits is going to help you out in the future. And don't lose sight about which forms are indeterminate and which are not indeterminate, because that's going to really determine what you do for these limits. So we'll see you next time, and have a good day.